Okay, I just want to quickly recap the logic. This is exactly what we're going to do to figure out what the conformal group is and how to work with the conformal group. So what have we got? We started off and we said we would like the group of transformations that preserves the metric. So that is an isometry. So that gave us the boxed equation at the top of this slide. And then we made an ansatz. We considered an infinitesimal transformation. We said x tilde mu will be equal to x mu plus zeta mu. For the top boxed equation to hold, we found the second boxed equation must hold. This was the killing vector equation. And we were easily able to solve the killing vector equation. That gave us the third boxed equation. So this is the set of transformations that preserves the Minkowski metric. From this, we were able to see that we have translations and we have Lorentz transformations. Once we had those transformations, we said, well, we know that any element of a Lie algebra will be written, any element of a Lie group will be written as the exponential of I times a parameter times by a Lie algebra element. And if we consider an infinitesimal transformation, the element of the group becomes 1 plus a term proportional to the Lie algebra element. And writing this down explicitly, so we gave the Lie algebra elements the names P rho and M mu nu. And writing down this explicitly, we got the equation in the yellow box. So the first, well, this term in the yellow box just came from applying what we know about the Lie group. And this term inside the yellow box came from thinking about our specific transformation that we had solved. And by equating the two, we've now managed to get hold of the elements of the Lie algebra for the Poincare group. So we've now got the Lie algebra elements. What we now want to do is we want to calculate the Lie algebra itself, and that means we want to calculate these commutators. So we could calculate a commutator between P mu and P mu and see what is this equal to. Another commutator that we could consider is the commutator between P mu and M, let's say, alpha beta. And then finally, we could look at the commutator between M mu nu and M alpha beta. Now, one thing that is worth saying is the following. We're going to be calculating these commutators using the expressions for the Lie algebra elements that we've just found. But when we get hold of the Lie algebra, that's now a very general equation. It's a set of equations. It's not tied in any way to the specific representation that we find. So it's not tied in any way to the explicit Lie algebra elements that we found in terms of derivatives on the coordinates. And then if you find any set of objects that obey these commutators, those will give you another representation of the Poincare group. And in particular, to do quantum field theory, you would be looking for representations of the Poincare group on the fields of the theory. So once you've worked out the Lie algebra, you have an extremely general statement actually defining the group, and you can look for representations of that group on fields or whatever else. Okay, so that's the logic, and we'll be applying precisely this logic to determine the conformal group. Okay, so now let's go ahead and calculate this commutator. It's no big deal. So let's just do that. So we want to calculate the commutator of P mu with P nu, and it's always useful to think about this as acting on some test function f, and at the end of the calculation, we'll drop f from both sides. Now let's just write down everything. So we'll have the commutator is P mu, P nu minus P mu, P mu. That's just the usual definition of the commutator, and both sides are acting on this function f. Now let's plug in everything. So we're going to have a minus I d by dx mu. That's for the P mu. we'll have a minus I d by dx nu for the p nu acting on F minus I d by dx nu minus I d by dx nu. So completely trivial, I didn't do anything. Minus I times minus I is a minus. So we've got the second derivative of F with respect to x nu. And then minus I times minus I is a minus times that minus is a plus. The second derivative of F dx nu. Okay, dx nu. But partial derivatives commute. So this is 0 times F. So very simple computation. Now all that we do is we drop the F off the first and last steps. So you've got P mu, comma P nu, that commutator is equal to 0. And that gives us the first commutator in our Lie algebra. Great. We'll continue in a moment.